x plus 2x squared. So let's ask, does this span V, which is polynomials of degree less than or equal to 2, as well? So to check, we'll write multiple of this plus multiple of that plus multiple of the third thing equals our typical element. So C1, 1 plus 2x plus 3x squared plus C2, 1 plus x squared plus C3, x plus 2x squared equals a0 plus a1x plus a2x squared. Then again, we'll compare the constant terms on both sides, the coefficients of x on both sides, and the coefficients of x squared on both sides. If we look at the constant terms, we've got C1 plus C2 plus 0 C3 equals a0. And if we look at the coefficients of x, we've got 2C1 plus C2 plus C3 equals a1. And then if we look at coefficients of x squared, we have 3C1, C2, and 2C3. That should be equal to a2. Alright, now this isn't a triangular system, so I can't just see the solution. But we can solve this using row operations. So this is 1, 1, 0, 2, 1, 1, 3, 1, 2. With a right-hand side of a0, a1, a2. So we're wondering if this system has solutions. Well, let's take 2 times the first row away from the second row and 3 times the first row away from the third row. So row 2 becomes 2 minus 2 times row 1. Row 3 becomes 3 minus 3 times row 1. And then we get 1, 1, 0, a0. 2 minus 2 is 0. 1 minus 2 is negative 1. 1 minus 0 is 1. a1 minus 2, a0. And then 3 minus 3 is 0. 1 minus 3 is negative 2. 2 minus 0 is 2. a2 minus 3, a0. Then we can multiply the second row by negative 1 to get rid of the minus sign here. It might be nice to do that to the third row too while we're at it. So row 2 becomes minus row 2. Row 3 becomes minus row 3. And I guess I could just do that here. Make that plus and minus, plus and minus. Sorry, minus and plus on the other side. Alright, so now we've done that, and now we can take the third row and subtract 2 times the second row from it. 3 becomes 3 minus 2 times row 2. And that gives us 1, 1, 0, a0, 0, 1, negative 1, minus a1 plus 2a0. And if we take away 2 times this row, 2 minus 2 is 0. Negative 2 minus 2 negative 1s is negative 2 plus 2, which is 0. And then negative a2 plus 3a0 minus 2 times negative a1, which is plus 2a1, minus 4a0. So that third right-hand side is three a naught minus 4a0 is negative a0 plus 2a1 minus a2. Now this third equation is going to be problematic because we've got 0c1 plus 0c2 plus 0c3 equals this expression, which is not necessarily 0. I mean, I guess there's some values of a0, a1, and a2 that make this 0, but we're trying to solve the equation in a way that will work for all possible values of a0, a1, and a2. Since we don't have negative a0 plus 2a1 minus a2 equals 0, for all polynomials a0 plus a1x plus a2x squared in the space, that means that the proposed set does not span V. So there are some polynomials, a0 plus a1x plus a2x squared, that we cannot get by taking linear combinations of these. In particular, any polynomial whose coefficients don't satisfy this. Like x. X is 0 plus 1x plus 0x squared, and the coefficients negative 0 plus 2 times 1 minus 0 equals 2, not 0. So any polynomial whose coefficients don't satisfy this equation aren't going to be expressible as linear combinations of those three. So again, that proposed set is not a spanning set for V. We can't express all polynomials as linear combinations of those three polynomials. The end.